Hello everyone, welcome back to another episode of Pinnacle Academy. I am Sannel Patel, Director of Business Development and Marketing at Pinnacle Ozone Solutions and a chemical engineer. Today we're going to dive into something that's at the leading edge of water treatment innovation, nanobubbles. I'm joined by two experts from Moleaer and the global leader of nanobubble technology. Christan, Ference, who is the Global Product Manager at Moleaer, who's leading the nanobubble product development, who has a strong background in chemical engineering and water tech. I'm also joined by Sohali, Akhter, who's the VP of R&D at Moleaer with 20 years of innovation and also has a PhD in chemical engineering, who is an expert in water, materials, and nanobubble technology. Gentlemen, thank you so much for joining us.
Thank you.
Yeah, thank you so much for having us on today.
Thank you so much. So let's begin quickly. I want to try to dive into this nanobubble. So Christan, can you explain what nanobubbles are and why is there so much excitement about nanobubbles in the industry right now?
Yeah, certainly. And that's like a great place to start. So what Moleaer specializes in is primarily industrial and commercial scale systems to make nanobubbles. And nanobubbles are this really exciting sort of form of gas injection. Nanobubbles are smaller than about 200 nanometers in size, which means they're not visible to the naked eye. But we can make these out of air, out of oxygen, out of ozone, and other gases. And they unlock really interesting properties and benefits with water. And so what we look at from Moleaer is we look at it through the lens of unlocking nanobubble technology to increase either efficiency in process, the productivity of a process, or the sustainability of a process. And it's really incredible just how broad we can apply nanobubble technology, where we see applications for this in really more than 90% of where water is used.
And can you explain what nanobubbles are? And I know we talked about the size. Is this a molecule that is generated? Can you explain the method, if that's possible?
Yeah, sure. So I think it's really important to understand that Moleaer did not invent nanobubbles. Nanobubbles are a naturally occurring thing, and they occur in waterfalls, for example, or in crashing waves. But what Moleaer really has specialized in is taking technology which makes high densities of these nanobubbles and doing that very efficiently. Again, primarily commercial and industrial sort of sized systems, and unlocking sort of that natural power for water treatment. Mm-hmm. So, nanobubbles, as I mentioned, are broadly about less than 200 nanometers in size. So that's not visible to the naked eye, but they exist in extremely high densities. So you can think about like millions or even more per milliliter of water. And the reason that's really exciting is because the nanobubbles don't rise to the surface and burst, but they rather just stay in suspension. And when they stay in suspension, they can last in a liquid for days, weeks, even months, depending on the application. And so now you have two forms of gas in the water. You have that dissolved form, which I think probably most of your audience is fairly familiar with. And then now you have this suspended form in the nanobubble, which is gas in its gaseous form. And because of its really small size and very high concentration, you have extremely large gas to liquid surface area. It does allow for some really exciting properties around like reaction kinetics, for example. And also because you have the suspended form of gas and water, you do see an effect around gas stabilization, something that I think is really one of the exciting aspects around specifically ozone nanobubble technology.
Thank you so much. So a question for you. One of the things we hear most often, as also Christan stated, is gas transfer efficiency of nanobubbles, which is normally compared to like conventional diffusers and injectors. Can you explain how nanobubbles normally transfer into a gas and like why it matters so much?
Okay, so the nanobubbles are very small, right? We say 100 nanometers. So what happens is, as a result of the small size, the surface area is extremely high. It could be thousands of times higher than, let's say, a microbubble, which are like of the micron scale. Mm-hmm. So your interfacial area is very high, and your gas transfer is directly proportional to interfacial area. So what happens, your gas transfer rate is very high. That's the first benefit, okay? The second benefit that happens is nanobubbles, because of their size, they hang around. They don't coalesce and rise up, right? Mm. So what happens, your efficiency is also higher, meaning for the same amount of gas you inject, nanobubbles would give you more dissolved gas compared to, let's say, other bubbles, which tend to combine and get lost in the atmosphere. So your efficiency is higher. Your transfer rate is higher, efficiency is higher. The third thing that happens is the nanobubbles tend to stabilize dissolved gases in water. For example, if I have oxygen in the water, the oxygen, dissolved oxygen will tend to hang on, for a longer time, okay? It's going to hang around for a longer time and not escape the water. So this stabilization mechanism is another benefit that has been observed in a number of different applications. Okay, so that's the third benefit. The fourth benefit, which is not obvious, is nanobubbles spread the gas far and wide. For example, in a lake, down to the bottom of the lake, down to the nooks and crannies of surfaces or in the soil. So that's one big advantage, that nanobubbles go where other bubbles cannot go. Okay, so these are the four advantages which we say distinguishes nanobubbles from microbubbles and macrobubbles. Okay, and in all the applications that we face, all of these are operative actually at the same time. But the lake example I mentioned is because people generally cannot fathom, you introduce nanobubble at the top, how does it go to the bottom? Okay, and there are various spreading mechanisms that happen that takes it to the bottom.
Wow, thank you. So, Christian, I know we spoke about efficiency, and the nanobubbles have unique physical and chemical properties. Can you give us some examples of how these properties will be applied in today's market, like in agriculture, aquaculture, and even municipal? What type of real-life examples can we see?
Yeah, certainly. And Sohail, as always, did a tremendous job of explaining some of the fundamental properties or the science behind the nanobubbles. But if we take a kind of zoom out, right, and think about one of the initial comments that I made around looking at nanobubble technology as a method to increase either process efficiency, productivity, or sustainability, we can use this technology, as you mentioned, like agriculture or aquaculture, to address some of the just persistent challenges, I would say, with traditional ozone injection, whether it's the tight process controls that often need to be maintained with large-scale ozone injection processes, or perhaps the transfer efficiency. And transfer efficiency is something that we see come up all the time, where in practice, in theory, traditional systems can achieve very high, certainly traditional optimized systems can achieve very high transfer efficiency. But in practice, when you integrate those into a large commercial or industrial system, we often see it doesn't pan out. And so that's an area where using nanobubble technology, which can achieve very high transfer efficiencies without some of those really challenging process optimization constraints and balancing constraints, that's where we can really see dramatic reductions in, say, ozone usage in some of these agriculture or aquaculture applications, just because it's, say, much easier to optimize the nanobubble technology for high performance transfer efficiency.
And so what type of applications, I know we spoke about aquaculture, spoke about cooling towers, like what type of applications would you be, like the biggest visual standpoint, like what industry would you be like focusing on right now?
That's a great question. I think there's so many opportunities for nanobubbles, and it really does come down to, what is the right treatment for that process. So when I say what is the right treatment, I think it's an area where Moleaer really looks to specialize, is identifying the right sizing, for example, the right way to integrate that nanobubble generator, and then also the right way to treat, meaning what gas are you using? If you look at ozone, for example, what is that level of ozone that's required to achieve our treatment objective, and how does that align with sort of historical expectations on the required dose? That's the area where Moleaer really tries to dive in and provide that level of sort of process expertise. But broadly, I mean, again, as I mentioned earlier, I think at least right now we're aware of applications in over 90% of where water is used where nanobubble technology can be applied, beyond just the markets that I think are very rapidly adopting this, like aquaculture or agriculture or even wastewater. There are many, many more other applications out there for nanobubble technology.
Thank you. So I know we spoke about ozone a little bit, and as we hear, most of our audience is from the ozone industry. Let's take it to an ozone conversation. So Sohail, What are ozone nanobubbles and how do they differ from oxygen, air, or carbon dioxide in terms of nanobubbles?
Carbon dioxide is an outlier, because carbon dioxide is highly soluble and it has a natural acidic pH when dissolved in water. So it behaves a little differently. But in general, all nanobubbles have the same properties. Okay, they have a small size, they have a surface charge, and they have gas supersaturation. Okay, so from that perspective, they're all the same. They differ in details. For example, if you look at the surface charge, which we call the zeta potential on the bubble, ozone generally tends to have a little higher negative zeta potential, meaning more highly charged. Okay, and that is because of the particular chemistry that ozone has. Ozone decomposes and also generates OH radicals or OH ions, which tends to enhance the negative zeta potential on the surface of the bubble. So that's one big difference of ozone. The reactivity of ozone, so the other molecules are not reactive. CO2 has some reactivity, but oxygen air would not have so much reactivity unless pushed by external energy sources. But ozone, because it's so unique, it does have the ability to generate ROS, reactive oxygen species, like hydroxyl radicals, which then further accelerate the whatever chemical degradation reactions that's happening around the nanobubble. So basically, the answer to your question is ozone, most of the properties are the same, but the reactivity and the zeta potential is different. It's a little superior. Not little, reactivity is actually quite a bit superior. And this difference or this benefit translates to many applications like AOP and enhanced degradation, remediation of even metal ions or heavy metals, remediation of organic molecules. So the short answer is ozone is distinguished by its high reactivity and more negative zeta potential.
Could you explain? I know our audience may not know the zeta potential. Do you mind explaining that a little bit to our audience?
Sure, yeah. So what happens is when you create a bubble, the surface of the bubble actually attracts ions from the environment. It could be OH minus, which comes from the water, or it could be even calcium plus 2 plus magnesium. It could be sodium. It could be whatever ions are there. Thermodynamically, what happens is that these ions prefer the interfacial area of the bubble. So especially OH minus has a strong preference for being located on the surface of the bubble. And when that OH minus comes and settles on the surface, the whole bubble becomes negatively charged. And that's a very well accepted theory of how nanobubbles get charged, is because of the OH minus ions that are already in the water. Okay. Now, the way it's measured is called zeta potential. There's a whole history in colloidal science where this term zeta potential comes from. And it basically measures the average charge on a bubble in a solution.
When it has that charge, what does that charge? Is it able to react? And then if it has a higher zeta charge, that means it has a higher potential of reacting with the impurities that are in the water?
Right. So what happens is, you heard about like charges repelling each other and unlike charges attracting each other. And both are actually active in this scenario. So with the like charges, what happens if I have a ozone negative, they'll tend to repel each other. And by repelling each other, they prevent coalescence. Okay, so they prevent the dissipation of ozone by making bigger bubbles and then rising up and dissipating. So that's one benefit. The other benefit that happens is because of the negative charge of the surface, it can attract positively charged, let's say, surfactants or positively charged ions and actually gather them around the nanobubble surface. Okay, so this is now positive attracting negative. Okay, and then you can almost think of it as a carrier. Now have a cloud of positive species around my negative bubble, and then this could serve as a delivery mechanism. Okay, go somewhere and do some other reactions.
Okay.
So this is one a basic mechanism, which is also common in colloidal science, that this operates, and it's true for nanobubbles also.
Thank you so much for that. So I guess what's the advantage, Christian, on your side? How does ozone nanobubbles create added value in treatment systems? And in particular, is this in disinfecting, oxidization, or multi-pollutant removal? Like what do you see as the main value added?
I think that's a really interesting area where we see the science evolving and maturing very quickly, and then we also see the market and the interest for this evolving, maturing very quickly. Just to use a couple of examples, if you look at traditional ozone injection applications where we're looking to achieve, let's use aquaculture or irrigation, for example, where you may look to achieve a target ORP residual and hold that for a given amount of time. Especially as you get into large industrial scale systems, you're talking about a lot of energy that goes into that process, essentially a big CapEx investment for the equipment to make that happen. And so, certainly what we've seen with nanobubble technologies is that in many cases, we can reduce both the energy that's required for treatments in say, a large several kilo per hour ozone application. You reduce the energy by almost 50%, which is incredible for our customers, especially in aquaculture that have remote locations where energy can be very costly. But to go on, to play that out further, we've also seen that energy is a combination of a variety of different aspects in an ozone treatment application, but we can also reduce the amount of gas required to achieve that same residual. And that's can be a function of the nanobubble, not only of just efficiently getting that gas into the water, but also reacting efficiently with contaminants and even driving really strong separations in an application. So separations is something that I wanted to touch on a bit here, and I think this is something which is very powerful with nanobubbles. I mean, we've seen just very dramatic effects, both with just air alone, and then if we get in, we can look at a variety of different gases, including ozone. And in separations applications, I think that's a big component of what we look at is with the benefit of nanobubbles. And separations, we know ozone injection can be a function, or I should say pollutant removal is a function of ozone injection can be a function of both direct oxidation and also separations. And I've seen a lot of really interesting, exciting work come out in that space on both the efficiency of nanobubbles to oxidize pollutants just as the function of, say, getting that ozone into the water and high surface area for reactivity, but then also, and sort of going hand in hand here, drive separations of those pollutants where they can be pulled off in other mechanisms. So, yeah, I mean, sort of in short here, there's a dramatic process improvement that we've seen both in aquaculture. I mentioned the energy reduction, which is ultimately what the performance metric that our customers are measuring us by, because they have very well defined and often regulatory required process performance requirements. But then in separations applications, for example, that's where we can really look to push the frontier of what was even capable beforehand with traditional oxidation or separations processes.
And finally, Sohail, for those that are less familiar with Moleaer, can you tell us a little bit about the company's patent technology and how it enables this kind of performance? Can you explain a little bit about the patents and how many Moleaer actually has?
So Moleaer started doing business in 2017. So it's been for about 8 years. Okay. So in that time period, we have now about 14 unique issued and pending patents. Approximately half are what we call design patents, where you're designing a generator, and half of them is what we call application patents, meaning patents which cover certain way of applying nanobubbles in different applications, industries. Okay, so that's the kind of divide as of now. So in terms of generation method, our basic method or the original method is what we call the shear method, okay? Meaning there's a shearing action we use, which is velocity gradient method, by which we shear off the gas bubbles and make nanobubbles out of it, okay? We also have other generation methods. We have a magnetic method, we have a triboelectric method, we have a microchannel method, we have a solubility gradient method, okay? These are in various stages of development, and the way we use them is we match them to particular applications. So, low flow, high flow, clean, not clean water. That's how we would select a particular generation method. Okay. In terms of applications, we have actually quite a bit of variety of applications. We have patented or pending patent. Wastewater is a big one. Okay, where we have applications in dewatering. Okay. and also applications in anaerobic digestion. Okay, and we have patent filings in both. We also have patent filing in fermentation. How do you accelerate? Fermentation is a biological activity, biological process. Is very much operative in wastewater because there's a lot of biology. So we have patents in that area, fermentation area. We also have patents in electrode coatings. Okay, electrolysis, you have electrodes, you can put coatings, and those coatings are made by incorporating nanobubbles in the coating solution. Okay, and that enhances the electrode functionality. So we have the patents on that. Then we also have a patent application on filtration membranes, okay, filter membranes. These are cast membranes, and by incorporating nanobubbles in them, we are able to control the porosity, the pore size, and that affects your filtration efficiency. So we have those. So we have a whole number of application patents, and we kind of come up with like 2-3 every year. Okay. This is our current batting rate, so to speak, right? So, yeah. So in summary, about 14 unique patents divided almost equally between method and application.
Thank you so much. And my final question that I have to all my members that join me here on the podcast style conversations that we have here, what's one thing that you guys would like to share about Moleaer, about nanotechnology, or just water treatment as a whole? What advice would you give anyone who's looking into nanobubbles, or any advice that you want to give someone who wants to join the water treatment industry? Is there anything in particular that you'd like to share with our audience? I guess I'll start with you, Christian. Anything you'd like to add?
First, as it pertains to nanobubble, I do think this is a tremendously exciting technology. I often tell our team and others that, I think we're in the first, maybe the second inning of the nanobubble technology development. There's so many applications for that, those that we're directly going after. And Sohali, that you mentioned a bunch, both just in water treatment alone, but then many others where nanobubbles can be used as like a chemistry too, which is certainly a very quickly evolving aspect of the technology. Personally, see nanobubbles as the method to we talk about increase process efficiency, increase productivity, or sustainability. From our lens and from our customers' lens, I think that largely means like, how do we reduce the cost of an operation? How do we use less chemistry? These are the real questions that we get all the time. How do we increase sustainability? If you look at lake treatment, for example, where the status quo has been largely just applying chemicals in bulk, year after year, and look at nanobubble technologies as a chemical-free, truly sustainable way for treatment. I think there's tremendous opportunity there. So if you're a water treatment expert, I encourage you to investigate nanobubbles, see where they can be applied in your process. Reach out to us, especially if you're in agriculture and in aquaculture and wastewater and many other applications, and see how we can use nanobubbles in your process.
Same question for you, Sohali.
Yeah, I agree with Christian, actually. He covered all the important aspects that anybody starting or already in this area would want to know. The only thing I would add is, if you educate yourself, right? I mean, people have some misgivings about what bubbles are and stuff, but these are not bubbles, okay? We call them gas nanoparticles, okay? They behave like particles, they act like particles, they perform like particles, right? Mm-hmm. So if you are interested in intensifying your process, which Christian already mentioned, intensifying your process in a sustainable manner, okay? Nanobubbles basically gives you that kick, okay? Adds value without adding chemicals. Okay? So that's the way I would describe it. If you're in the water business and you are constrained by different, discharge regulations or constraints or cost, look at nanobubbles. Okay, it's going to intensify your process, reduce cost, basically produce value. I don't want to say out of nothing, but basically produce value out of taking gas or air or oxygen. Okay, so my advice would be, yes, dig into it, okay, clear your misconceptions, and then look at where you can intensify the value in your process.
Wow, that was amazing. Thank you both. So once again, thank you. This has been a fantastic, highly technical conversation, exactly what the Pinnacle Academy is about. Christian, Sohali, once again, thank you for sharing your insight and expertise. our audience, I guarantee, would love this type of conversation. To everyone that's watching, if you want to learn more about nanotechnology or ozone, or even just the future of water technology, reach out to Moleaer or visit the website moleaer.com or reach out directly to pinnacleozone.com. Thanks again, everyone, for joining, and we'll see you next time at Pinnacle Academy.